Recording this.
This is a
I will get a copyright infringement, but that's okay. So, here is the de Broglie wavelength. You can see we've got how many wavelengths there? 4. Okay, so that's n equals 4.
commonly known function of standing waves. Here we have a path with 4 waves. What would happen if the electron went to a higher energy level? Let's say from a path with 4 waves to a path with 5 waves.
Watch this.
The standing wave with 5 waves would have to increase in size to accommodate the 5th wave, and so this higher energy path is larger, and so this higher energy electron is therefore further from the nucleus. This is what Bohr had stated with his circular orbit model, but without explanation. Here, the size of the path would have to increase exactly to the point where another wave could fit into it. And so, the electron can only absorb the exact amount of energy that will allow it to move from one standing wave to another.
Alright, so not much different. So this could still explain the Bohr postulates, but instead of circular orbits, we're now looking at number of wavelengths that the electron can oscillate at. And obviously it agrees that the greater the number of wavelengths, the further out you were. And so they had figured out the approximate radius that the electrons were in the different orbitals. It still holds. Now you're looking at the electron not as a particle, but as a wave at that orbital distance. Okay, so this was the de Broglie wave, or the de Broglie model, or the de Broglie, depending on how you pronounce it.
Bohr's quantized electron now makes sense. Let's enlarge the new standing wave for the sake of clarity. So, if the electron has gained the exact energy needed to go from a standing wave of 4 waves to 5 waves, it will exist at a standing wave of 5 waves. This brings up the question, what if it absorbs some amount of energy that is not enough to get it to a standing wave? Let's see what would happen. The electron would not be in phase with itself. It would not exist as a standing wave. The electron would interfere with itself and could not exist on a path that was not in phase, a path that interferes with itself. This is a beautiful explanation of Bohr's quantized electron.
Okay, so there we go. You can't have it as n equals 3.4 or something like that. So that still agrees with the Bohr model that the electron can't exist anywhere in between n4 and n5. Same deal, if it de-excites from n5 down to n4, it spits off a quanta of energy known as a photon. So everything was working there.
A very important part of Bohr's model is that if the right amount of energy is absorbed by the electron, it can then go to a higher energy orbit. Here, the energy of red light is absorbed by the electron, which pushes it to a higher energy wave, but it would want to get rid of excess energy, and does so with the release of red light, while going back to a lower energy orbit. This explains the specific, discrete colors coming out of energized elements. For de Broglie, if the right amount of energy is absorbed by the electron, it can then go to a higher energy standing wave. Here, the energy of red light is absorbed by the electron, which pushes it to a higher energy standing wave, but it will want to get rid of excess energy, and does so with the release of red light while going back to a lower energy standing wave. The electron cannot absorb any other energy, for example yellow or blue, because those colors do not have the energy required to get the electron to another standing wave. This explains the discrete colors coming out of energized elements. Bohr was correct in his remarkable application of quantized light to a quantized electron, which was subsequently shown to be correct through de Broglie and the current quantum mechanical model, and many experiments confirming that electron energy is not continuous but discrete. The electron can only exist at allowed energies, and so
Energy is quantized. So the Bohr model hasn't been thrown out, all right? It still works, it's just been improved slightly, okay? So none of the de Broglie postulates or Schrödinger or Heisenberg, nothing what they've suggested is going to discard the Bohr model. It's just adding more stuff about how particles can act as waves. Okay?
we say the electron energy is quantized. So, de Broglie succeeded in describing a mechanism in Bohr's hypothesis of electrons only existing at allowed energies. This established the wave-particle duality of matter, a monumental step in our current view of the universe. It earned de Broglie the Nobel Prize in Physics in 1929, only 5 years after its publication as part of his PhD thesis, and was a critical step in establishing the quantum mechanical model of the atom 2 years later by Schrödinger and Heisenberg, a model which is intimately based on the wave properties of the electron devised by de Broglie. The electron's wave property presented in this video was de Broglie's interpretation of the mathematics he established to describe this wave-particle duality of the electron, but it is in fact very different from the now more established interpretation of the electron as wave.
Okay, so let's just stop there. If you recall back to the Brian Greene video of him throwing the electrons down the bowling alley through the double slit, yes, we all saw that. Good. We were in class, it did happen. We're saying that even if you throw one electron at a time, it doesn't appear directly behind each slit, like firing a machine gun of bullets through two gaps. You don't get those two patterns. You get interference. And so what they were saying is that when the electron's moving, it's acting like a wave. It has a de Broglie wavelength. And then the current understanding with Schrödinger's model is that you've got a probability density. So what we're seeing here is a probability function of where you're most likely to find the electron in the nucleus. Now, it's the same idea as when you fire the electron down a bowling alley. There's an equation called Schrödinger's wave equation. It's a probability that you'll find the electron in one spot compared to another. But if we look at the electron orbiting the atom, here you can see that the bright blue is a high probability that you'll find it there. The dark is no probability. The bright again is a high probability in the next energy level. So again, this is still in agreement with Bohr, that the electron can't exist in between. But now we have to understand when things are moving, we are not certain about where they are. So we can measure its speed with high certainty. We know how fast the electrons are traveling if we treat them like planets around the nucleus, but we don't know where they are. All right? You won't be able to know both where they are and how fast they're traveling to a high degree of certainty. So this is the probability density, okay? And this is now at the current model of the atom. But really, we stop at Bohr and we just dip our toes into the de Broglie model. In a WACE exam, it would be calculate the de Broglie wavelength of a proton traveling at this speed. How might you detect it? Well, you pass it through a gap of an appropriately sized spacing, or a similarly sized spacing. That's about as far as you're expected to do in an exam. Huh?
So we don't really need to know about kind of how it exists in a probability wave? Or?
No, but I'm going to spend maybe 20 minutes beyond the syllabus, but it still is confirming and in agreement with what Bohr was saying. Okay, let's just keep going. I've got a couple more videos.
In 1926, Max Born interpreted the standing wave of the electron to represent the probability of where an electron is within the atom.
Brandon, close it, please.
One last fun bit about de Broglie. When he presented this work to his PhD committee, the Mathematics Establishing Wave-Particle Duality, the committee could find no fault with the math, but they had great difficulty accepting an electron behaving as a wave. To help make their decision of whether to give de Broglie his PhD, they sent off de Broglie's dissertation to Einstein, who wrote back and told them that the idea had merit. So, de Broglie got his PhD in 1924, 1926 saw the establishment of quantum mechanics, and in 1929, the Nobel Committee also thought his idea had merit. Thank you very much.
All right, and they clap. Now, things are not what they seem. This is a very brief snippet from the Royal Institute Academy, very famous society in England. They do lots of presentations and lectures. This bloke is talking about the weirdness. Now, he started the first half of this lesson as just an intro into light and the double slit experiment that Thomas Young did in the 1700s. And everyone's like, yep, that makes sense. Interference, yep, bright regions on the screen, positive, dark regions, destructive. That all makes sense. But then he goes, let's do the same experiment with particles. Let's fire particles through a double slit. And then that's when they start acting like waves. So I hadn't loaded it up into the correct spot, but I'm just gonna find here, I think. Let's go. Go, buddy, go.
Which is why you get a bit of a spread. The first mystery of quantum mechanics comes when we open the second slit. Because now we see something that's very much like the interference pattern we got with light. Rather than having two bands of spots where the atoms have gone through the two slits, it's as though the atoms have gone through the slits behaving like waves. And you get interference of the waves and you get these bands. If we know nothing about atoms or quantum mechanics, you could try and rationalize it and say, well, you know, maybe atoms behave in a very strange way, and only a certain number of them are allowed to all sit together. And so, you know, me and my gang, we're all going to go on this slit. No, sorry, no room for you. You go the next slit above. And by the way, there's this rule that no one can go in between the two bands, but a few naughty atoms do. So there's a bit of a scatter. You know, we don't. There could be some forces between atoms that make them coordinate their actions in a way to give this pattern. That's not mysterious. That's just, we just don't know how atoms do things. But we can be clever, and we can force the issue. What if we were to not send the atoms all through at once, but send them through one at a time? Leave enough of a gap for the atom to get through to hit the screen. Of course, as I say, some atoms will hit the first screen and not get through, but those that get through will hit the back screen. So let's run the experiment again slowly. And gradually you'll see, as the atoms go through, they'll look like they're just randomly arriving on the other side. You keep sending atoms through one at a time, and gradually that same pattern appears. So each atom by itself is somehow contributing its small part to the overall wave-like behavior that we see in the interference pattern. How does it do it? How does... We know the atom's a tiny, localized particle. We can't see it. It's too small to even see under a microscope. We're firing it at the screen with the two slits. Some moment later, you see a flash of light on the back screen. It's arrived in a localized point. It's not spread itself out. You don't get like a wash of sort of a faint light across the whole screen. It's a little point. The atom is localized. It's arrived in a certain location. And yet, it somehow seems to have been aware of there being two slits, not one, because it's given rise to this interference pattern. How does one atom do that? Does it split in half? Does it become like a cloud that goes through both? Well, we can try and be even cleverer. What if we were to spy on the atom and see where it goes? We can gently just observe which slit it goes through.
Okay. Now,
so you put
I'm just going to mute him now
just above the upper slit that will flash or beep whenever it sees an atom go through that top slit.
Okay, and every time an electron passes through.
Sure enough, you fire the atoms through one at a time.
But this is a problem.
50% of the time, the detector
one of the rules
will
is
beep.
Heisenberg's uncertainty principle.
The other
Just draw
50% of the time it doesn't,
It's
the assumption being
momentum
that the atom
and
has gone
position
through
can never be less than
the lower slit.
H on 4
But of course, I've been
pi,
cheeky here.
H
I
on
haven't
4
shown
pi
you
is
the
a very,
results
very
of the
small number.
experiment.
But here's the problem. If we increase our knowledge
what you
of
get.
where a particle is,
50% of the time, it beeps, and you see a spot arrive adjacent to the upper slit. The other half of the time, it doesn't beep, but you see a spot arrive at the lower slit. So, yeah, it's picked out the atoms that have gone through the upper slit, and not the ones that have gone through. So each atom does go through one slit or the other. But that's a different result to what we had earlier. So here's the last bit of sneakiness that we can play with atoms. Surely now, you know, we're going to get to grips with it. Leave the detector there, but just very quietly go and unplug it. Don't let the atoms know that you're not spying on them. Make them think that you're still detecting them. So, yeah, okay, we're going to run the experiment, atoms, okay, get ready, one at a time, we're going to be checking on you.
This is
all right,
really
so
weird stuff.
Run the experiment
but it
again.
Works. So he goes, the strange thing is, you monitor the top slit and you suddenly get the two bands. It's as though the electron is acting as a particle. So see how we put the monitor there? You're essentially putting it here. It was a difficult experiment. By monitoring it, it manifests as a particle, and if you stop looking, it suddenly acts like a wave, and we get the wave pattern appearing on the screen. Yes, J-Bob?
Is that sort of the basis of Schrodinger's cat?
Yes. I'm just going to go back. We've got one more video, but I'm just going to go back to what I wrote down, and I wrote it down wrong. All right. Okay, so I'm just going to delete. I don't think I can delete that. Hang on. Draw, erase. All right. I had it wrong. It's 4 pi. All right, there we go. Now, oh, geez, don't want that. Undo. So, yes. Basically, even with this, let's just do a few examples of Heisenberg's uncertainty principle. And it comes down to the wave-particle duality. They had to come to an agreement that in the quantum realm, quantum mechanics, things are weird. Classical mechanics don't apply. Particles can act as waves, waves can act as particles, and we need both models to be able to explain phenomena, okay? And it depends on what the experiment is. So, for example, with an electron orbiting a nucleus, Heisenberg's uncertainty principle works here because we know how fast the electron is as it's orbiting, but we don't know where it is. Okay, so we can be really, really precise with how fast it's travelling, but we've got no idea where it is, and that's why it's a probability wave. Then, here, this was the electron diffraction. Okay, so this is the pattern that the gentleman was talking about that was shown on the screen. Basically, if we're accelerating our electrons, we know their speed, but we don't know where they are. That's the whole Heisenberg's uncertainty principle again. We know exactly how fast our electrons are travelling because we know how much energy they have, but we've got no idea where they are until they smack into the screen. And what what Schrodinger said was, in order for us to measure its position, it has to strike the screen, and then we know its position, but we don't know its speed. That basically, the simplest example is, the wave equation that Schrodinger had obviously looks very similar to this kind of shape, and it's very crazy mathematics. It's a probability equation. High probability in some regions, low probability in others, and it requires the de Broglie wavelength, which depends on its mass and its velocity, and Planck's constant, okay? So, what they say is when the electron is detected on the screen, Joseph Bonadeo, the probability wave collapses and the particle then manifests itself as a particle, and we see it as a particle. But before then, we can't treat it as a particle right there travelling with this speed, and in the next microsecond it's going to hit there. We don't know where it is. And in order for us to get an understanding of the equation, we can't just use one atom. You need statistical mechanics. You've got to look at how billions of electrons behave. And once you get billions of electrons, you can then sort of figure out a probability. It's the same as radioactive decay. You can't point at one radioisotope and say in 3.5 seconds it's going to decay. Okay? So, back to Schrodinger's equation, probability. You have to accept that electron is in all possible positions, and we won't know until we detect it. But once we detect it, we lose some information. Okay? So the idea of Schrodinger's cat, he tried to explain his equation to the layman, the person in the 1920s that didn't have a physics degree. Okay? He said, all right, pretend that there is a cat in a box, and in the box is a vial of cyanide, poison. And next to the box of cyanide is a detector that breaks the vial if it detects the decay of a radioisotope. The radioisotope has a half-life of T. And so in T seconds, you start your clock. Tick, 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 tick. Once you get to T seconds, you know that there's a 50-50 chance that radioisotope decayed. spat out a particle, the detector detected it, the vial broke, and the cat died. But until you take an observation, both states of the cat, both live and dead, are equally possible. So you say that the cat is not a particle, it is a probability wave. And the only way that you make, once you make a measurement, one of the probability waves collapses into reality. The cat is alive, there it is, meow meow. Or you open it up, oh crap, the cat is dead. But until you make an observation, Cameron Garside, the cat is both alive and dead. It's like saying, until the electron strikes the screen, it is everywhere in this probability wave. We know how fast it's travelling, but we don't know where it is. Okay? We can look at the other way. We can look at where it is, but we don't know how fast it's travelling. And Derek from Veritasium is going to show us. And then the netball people can go. But early Derek.
Today, I'm doing an experiment that demonstrates Heisenberg's uncertainty principle.
All right.
So here I have a green laser, and I'm firing it down towards the front of the room through a narrow slit. Now that slit can be adjusted, so it can be made narrower or wider.
Now, guys, this is diffraction. This is the spreading out of light as it passes through a narrow gap. You learned that in year 11. We learned that at the start of the topic. It's a wave phenomenon, right? Light, wave, yep, does it. But let's just look at it from a different perspective.
And the laser spot is projected onto a screen behind it. So what do you think is going to happen to this spot on the screen as I narrow the slit? Well, let's have a look. You see exactly what you'd expect. The spot gets narrower and narrower. The sides are getting cut off by the slit. Makes complete sense. And if you stop there, you would never realize that Heisenberg's uncertainty principle is at work. But if you keep going, something strange happens. As you make the slit even narrower, the spot starts to spread out. Isn't that incredible? You're making the slit narrower, and yet the spot on the wall is getting wider. The narrower you make it, the wider that spot on the wall becomes. To understand this, we have to look at Heisenberg's uncertainty principle. Heisenberg's uncertainty principle is normally written as delta x delta p is greater than or equal to h on 4 pi. So what does this mean? Well, it's about the position and the momentum of a particle. So x is the position of the particle and p is its momentum. So delta x is the uncertainty in position and delta p is the uncertainty in the momentum. Now, if you multiply those two quantities together, they must always be greater than or equal to h on 4 pi. Now, h is Planck's constant, and that deserves a video all to itself, like this one by 60 symbols. But for our purposes, it's just a very small number. So in our everyday lives, we don't come up against this uncertainty relation because everything is much, much bigger than h. But as we narrowed the slit, we were decreasing delta x for those photons. So we were getting more and more precise about where the photons were passing through that slit. And at a certain point, you come to this limit, so that if you narrow this any further, you're going to break this uncertainty relationship. So what needs to happen is the uncertainty in momentum needs to go up. I should specify this is uncertainty in momentum in the x direction, in the horizontal direction. So if before photons were going perfectly straight, now they must veer off to the left or to the right to ensure that we don't break Heisenberg's uncertainty relation. And the more you decrease your uncertainty in position, the more narrow you make that slit, the more the uncertainty in momentum has to go up. And so if these photons are going to the left and the right, that's going to produce a much wider beam. It's really, really non-intuitive, but it's the way the world works.
Must be the sun.
So, this uncertainty principle pops up everywhere, and it hasn't been violated. Einstein used to try and think up thought experiments because obviously you're trying to take measurements of momentum that are so small that they're immeasurable. He would do these thought experiments where imagine you had a photon of light bouncing backwards and forwards in a box, and you open up the door and the photon travels out and it's sitting on a set of scales. Of course, you'd never be able to complete this experiment, but even he himself, at one point, there's some really great stories about his, not quarrels, but sort of rallies with Bohr and de Broglie going, I reckon I can think up of an experiment. Suppose this. And at one stage he thought he had one that violated or at least contradicted the Heisenberg uncertainty principle. And he put it out there, and he'd actually made a mistake that he hadn't considered either special relativity or general relativity, so his own sort of ideas, into this thought experiment. And when he factored them in, boom, it cancelled out, and you went back up to being above h on 4 pi. So lots of really interesting thought experiments that he proposed. Even in particle physics, if I can remember when we get to it, you can fire... No, hang on, let me try this. You can have high... Yes. I've got it. Mass and energy, right? It's E equals mc squared. You can't get any more energy than what mass you have, and you can't make any more mass than what energy you put in, right? So Einstein said that energy and mass are equivalent, and they're related. E equals mc squared. Mass is also energy divided by c squared. What they found was, if you have a high energy particle coming in, lots of energy, it can collide, and for a brief moment in time, it makes a particle that has more mass and energy than what was put in. But then that particle doesn't live for long enough, and it decays back down into smaller particles. And normally you'd say, well, that's breaking all the rules. But it turns out that it lives for such short distance and time that it's allowed within the Heisenberg's uncertainty principle. So even particle physics, in high energy particle accelerators and colliders, you normally go, that shouldn't occur, but it doesn't occur for long. It occurs for like a nanosecond, and when they worked out the maths, it turns out that even still, it was allowed because it was sort of hidden within the uncertainty principle. I'll try and find, I think I have a page on this rare exotic particle that wasn't thought to exist but actually does. I'll try and find it when we get to that topic in week 7 and 8, I think we do it. Alright, that's me done with Schrödinger and Heisenberg and de Broglie. Now you have the back of your booklets, has all of that. The chapter review, look at them. The chapter review does everything, guys. It's waves and particles and Planck and Bohr. It's got refraction, it's got diffraction, it's got ripples of waves. Please get those questions done. Next week we start relativity. We've got 5 weeks left. We do have to race through this, so it is essential that you do this work. We're going to be spending 1 week on a topic that I would really like to have 2 weeks. Okay? Ideally, I'd like to have double the time. So please get that done, guys. And I'll see you on Monday with our new topic. All right, see you later.